Welcome you to these lectures on fluid mechanics. As we discussed in the last classes, the fluid at the rest, which is very simplified cases we discussed, and today we are going to start very interesting subject on the fluid mechanics, which is called fluid dynamics. Very simple way we will try to understand the complex fluid flow problems using Reynolds transport theorems and the control volume concept. So, today lectures I will focus on systems versus control volume concept, as well as I will talk about the Reynolds transport theorem, which is very unique theorems, simplifies very complex problems, and we try to solve the fluid mechanics, the problems what we see get it from this. Let us have again the reference books what we discussed is also earlier the Sinjal Simbala book, which is having a lot of illustrations of real practical problems, and that what is apart from giving a mathematical treatment of the fluid mechanics, also it indicates that how complex fluid flow problems happens in natural conditions. And the FM White book, which is concise, mathematics driven with few illustrations, and another the Indian books on fluid mechanics by Professor Vidyasagar Pane. Let us start it in the last class. As I told you, we discussed about the fluid at rest, which is very simplified, that we know how the buoyancy forces happens, and the basic concept of the Archimedes principles, as you know it. Again I can repeat, a body immersed in a fluid experience a vertical buoyant force which is equal to the weight of the fluid displayed by the body. That is what you experience it when you dip in a swimming pool. So, or a ship floating in a river or the oceans. So, these Archimedes principles are hold coded for a simple day to day life what we experience it, but if you go to the micro scales, like the water vapor transport process what it happens it, which is the major process for the global climatic circulations pattern, that is also follow simple buoyancy law of the water vapor transport mechanisms. So, with that also we discussed that what is the stability of the floating of bodies, unstable, stable or naturally stable conditions, that with respect to a relationship between metacentric height and the CG, the center of the gravity. Based on that we can tell it if floating bodies whether at what condition, whether it is a stable or unstable or natural equilibrium conditions. Then we also simplify the conditions, like if you have a uniform rotations of a half filled liquid containers, what could be the pressure diagrams, what could be the height of the liquid will be formed when you rotate with uniform angular rotations. Also we discuss about the control volume with moving with a constant accelerations, which is the rigid body motions of oil tanker, or even if you can simplify that conditions to find out the sloshing behavior of any water tank during the earthquake motions. So, those concept, even if it is a simple concept, but those concept also sometimes we can use it to derive the force component due to the pressure and the gravity force component. So, as of now, when the fluid is at the rest, we talk about two forces component, that the force due to the pressures and the gravity force. Now, as we are moving to the next levels, which we talk about fluid in motion, that is what to simplify it. I will today cover first what are the real challenge today we have been facing it, giving a simple examples. Then again I will talk about why do we need the virtual fluid ball concept. As earlier I said it, this is a new concept. I brought it for the students to visualize the flow, and once they visualize the flow, they can solve the problems. That's again I am to repeat it, the virtual fluid ball concept, because that's what is necessary to choose appropriate contour volume to solve the problems. So that's the idea behind the virtual fluid ball concept. That's what I will repeat it in this lecture also. I will discuss, as I have given earlier, the definitions of system and contour volume. Today we will discuss more detail on systems and the contour volume. Then I will talk about the types of the contour volume, and we will go to the Reynolds transport theorems, which establish the relationship of physical equations in system level and the physical equations at the contour volume level, which is a great equations. There is a great simplified equations which integrates all type of the fluid flow problems through the Reynolds transport theorems. We can solve it, and then I will have a summarize the content of today's lectures. Let's come to challenge in the fluid mechanics. If you look at the report what is Indian Express in January 27, 2018, it says that it has something like 12 major accidents happens to the helicopters took place between almost 8 years in the eastern Himalayas, particular to Arunachal Pradesh, which lost 55 people. Now the problems is coming at that why do you have so many major helicopter accident over Himalaya? Let us understand what is eastern Himalayas. The eastern Himalayas, if you experience, if you can see it, really it's a different the altitudinal variations. That's what is altitudes varies from 200 meter to 3000 meter in a width variations of 100 kilometer to 200 kilometer. So large variations of altitudes happens with a aerial distance of 100 kilometer to 200 kilometer, and there is a complex Himalayan terrain. So today you can visualize how three-dimensional Himalayan terrains are very complex, that you can now we can visualize it. When you have very complex Himalayan terrains, you can expect it that the weather will change drastically from time to time. As I visited the Tawang regions in eastern Himalayas, I saw personally that the weather changes within a few hours. So when you have a weather system is so dynamic, it changes from sunny weathers to the snowfalls, the thunderstorm type of formations happens it. So you have a lot of the systems of changes, the pressures and the velocity fields. That's what we don't understand it. When you have in a complex terrains, when you have the heat energy exchange and the vegetation's interactions, how this weather is changing it, that knowledge also we have a limited. When you have a very drastic change of the pressures and the velocity distributions about these the helicopter systems, okay, which was never tested to do for the Himalayan terrain, it can experience the lift and drag force which was not used to design this. Not only that, we can expect it that there could be a macro turbulent structures, the formations happening it, which we don't have a knowledge, and those combinations of macro turbulent structure and changing this pressure and velocity field, causing the different direction of lift and drag forces. Because of that, most of the pilots, they failed to control the helicopters, and because of that we had these 12 major accidents, and that what within 8 years caused in eastern Himalaya. So, if you look at this problem is a fluid mechanics problems, and we have not studied or we do not have a knowledge of so complex weather systems is a part of the fluid mechanics, and even if you have a very robust helicopter system which crashes as usual. So, if you look at these problems, it is a really challenging problems. Still we have a challenge the fluid mechanics problems, as I said it a simple examples giving it that the crashing of the helicopters in Himalayan regions, that because of the weather systems which it changes very fast, and that weather system changes the pressure and velocity field so drastically, and that what might be there be major macro turbulent structures. That is the reasons it is the place that. If you heard about the crashes, the fighter plane crashes over the eastern Himalaya in World War II, also we can have the same assumptions is that the change of the climatic systems what had happened in during the World War II, that what is never understood it, that might be the one of the cause. There was lot of crashed weapon during the World War II in these regions. So, the fluid mechanics is an interesting subject. No doubt it is a basic course we will talk about in a basics level, but my suggestion you to read the fluid mechanics to solve, which is real life at present what we have been facing it. Now, as I said it earlier, to understand the fluid mechanics we should have the concept of virtual fluid balls, which is a new concept as I said it earlier. And if you look at considering these, I will discuss you the difference between system and the control volume. So, as I told earlier, I am just looking at a virtual fluid ball concept where this type I have the hills, I have the radar towers, and this could be expected velocity distributions having 150 km/h speed. Okay. So, you can understand it is a very simplified case, as I gave an example of helicopter crash, but this is quite simplified case that I have only one directions velocity distributions and which could be higher of a order of 150 km/h, and we need to design these radar towers. Okay. So, if you look at that, this is very challenging fluid mechanics problems, but analytically simplified way if I am to compute it. What I will try to do it that these towers I can represent as a small ball, okay, a spherical ball, and I will have a virtual fluid ball concept to find out what could be the diagram of streamlines. Okay. If I draw the streamlines, then I can tentatively know what could be the force is going to happen, the lift force and the drag force, the Fd and Fl, this lifting force mechanisms and the dragging force. This is quite simplified one. Okay. To have a finding out just ruling the virtual fluid balls and try to find out what could be the streamlines, because we know the streamlines we can tentatively know the pressure distributions, velocity distributions. As we know the velocity and pressure distribution, we can integrate the pressure distributions over this object to compute what will be the lift force, what will be the drag force. Again I tell you, it is a simplified version, but for a real field we can solve these problems either computational fluid dynamics or conducting the wind tunnel test. We need to do that part. Okay. But as these lectures, we will just talk about how we can simplify the complex problems and use analytical methods to solve the problems. That what my responsibility for this course, but visualize the fluid flow problems now as I can understand it. Any of the students have a lot of resource now to visualize the flow. Lot of materials are available in YouTubes and all. You can visualize the flow, and visualization flow is more important as compared to as well as to know it the analytical approach of solving fluid mechanics problems. Now, let us discuss about the system versus control volume. What is a system? What is a control volume? And how you simplify the fluid mechanics problems. Now, if you look at, there is a airfoil, this is a pumping systems and the turbulent systems. Okay. We can define it, a systems and the control volume solve these problems. Okay. To know the performance of the pumping systems or the turbulent system or the airfoil. Okay. You know, it is a very basic concept of the airfoil used for designing any aircraft. So, the aircraft wings looks the cross sections like this. The streamline flow and the pressure distributions gives us what could be the drag force and the lift force. Based on that, we design a fuel efficient aircrafts. So, the designing a airfoil is a very interesting thing. How to design the shape of the airfoil, so that we can have maximum offlet and also the drag force will be the less. That is the way we tested the performance of the airfoil or the pumping systems, or the, if you look at this the pump belt or the turbine blade, those are also work like the similar concept what we have seen in aerofoil conditions. Now, let us commit that what is the systems, what is the control volume. Okay. I will just now talk about to same virtual fluid ball concepts, but if you look at this, when you talk about systems, that means we define as a group of the set of fluid particles. That is what is common definitions. What is a control mass or the systems? That means it is what we consider a set of the fluid particles. But now I tell it is not a set of the fluid particles. We are talking about set of virtual fluid balls. Okay, VFV. Okay, virtual fluid balls. Fluid particles are the fluid balls. That means we define there are n number of virtual fluid balls as a system, and as they have in motions, they change the positions, they changes the velocity vectors, they changes the pressure vectors. Okay. So, that means you can see that there is a systems means is the collection of n number of virtual fluid balls, or other way around, a set of the fluid particles. That is what we define in that. But when you talk about the control volume, we talk about a region of space. Okay. That is the basic difference. It is a space definite. Okay. It is not related to virtual fluid ball which is having a motions. The space can have a motions, but we define the space which is the control volume. Okay. So, that means we are at the space level, that is the particles level. When you have defined the space, that means you have the control surface, you will have a control surface. You can see these figures, you will have the control surface. Through this control surface, the fluid balls will come in and go out. So, there are the control surface, there is no exchange of the fluid balls or the fluid particles. Same way, there will be a control surface through which we will have a fluid will come into this control volume. There will be the surface, from that the fluid will go out. That will be the outlet. So, influx and outflux. So, that means you can understand it, the systems and the control volume. In a control volumes, we talk about a region of the space, where is in a control mass, we talk about like a fluid mechanics or a virtual fluid balls, they are coming it and a group of the fluid balls I have considered it. That is what is this interesting figures, what is showing it, that if you tell it the system at the T1 time and control volume at the same times, that means whatever these number of the fluid particles are there, that is what is my control volume at the t equal to t1 time. But if you look at the time equal to t2, where the control volume, if it is a fixed control volume, if it is a fixed control volume, okay, then we will have the control surface remain the same, the control volume will be there, but the system which composed of n number of the fluid particles or virtual fluid ball, they will be at time 2 in this place, maybe they are disintegrated, okay, like 2 pieces. So, the systems is dynamic, the giving examples of that n number of the fluid balls, virtual fluid balls are coming it. After T2, they will be in a different space, they may disintegrate, they may have a different location. But the control volume, what we talk about, that if it is a fixed control volume, it remains at that space, and whatever coming into and going out at the fluid particles level, we do not look it, but what we look at, because of these the fluid particles coming into the control volume, what is the change in the velocity field here, okay, velocity factors, and the mass flux, okay, how much of mass coming through the surface, mass flux, the pressure gradient, momentum flux, energy flux. So, we do not bother about the fluid particles, the movement of the fluid particles, we bother about that because of these fluid particles, the transport mechanisms happening through this control surface, how the velocity distribution changes, the pressure distribution changes, mass fluxes changes, the momentum fluxes changes, energy fluxes changes. So, the problems is quite easy as compared to do at the system level. That is the reasons we work at the control volume level, where we can define the surface, through that there will be mass exchange, momentum exchange and the energy exchange, and because of that there will be a change of velocity distributions and the pressure distributions and the temperature distribution, as I do not focus more on compressible flow here in these basic levels. All these the field variations of the density, temperature, the pressure and velocity, that the effect we find out because of the transport mechanisms of the fluid particles or the n numbers the virtual fluid balls which is going through these ones. So, try to understand it is a flow systems. When you use the control volume, we try to find out not to track individual fluid particles what is happening in, but to get it because of this fluid particles movement, what could be the change in pressure distributions, in velocity distributions and also the cause the mass flux, the momentum flux and the energy fluxes. That the concept what we should build it, and we should know it how to define the control surface. No doubt I will deliver these lectures of the fluid dynamics which is there in FM White book or Sinjal Simbala book, more than 5 to 6 lectures. Try to you to convince the basic concept of this system control volume. If you understand system and control volume approach, and if you have a art to use the control volume concept like free body diagrams in solid mechanics, you can solve many problems very easy way. What I am to say it, as you are trained to use the free body diagrams to simplify the complex solid motions, the force components, exactly this the knowledge of the control volumes, velocity and pressure diagrams approximation, the streamline patterns will help us to solve the complex problems in systematic order. Considering that, I will emphasize more on control volume concept. That what is my objective, and I have designed this course such a way that you should have a more exposure to control volume concept. And if you understand the fluid control volume concept, really you can solve the problems we have been facing in natural sciences, the designing of any hydraulic systems and all, and especially the problems we are facing in present 21st centuries. Let's come back to the topics. Okay, what we should have this the types of the control volume. As I given in the first, that if I have a nozzles, okay, the flow is coming in and the going out. Okay, flow is coming in and going out. As if I having a V1 velocity, definitely the velocity V2 will be different. There will be a change in energy, change in the momentum flux. That what will give a force on this system. So, to find out what could be the force acting on these systems, we can use a fixed control volume having influx of velocity here and outflux of the velocity V to find out what could be the forces, what could be the energy losses. So, we use many of the time fixed control volume. That means, the control volume space does not change with the time. The control volumes remain at the same locations. Fluids are coming in and the going out. So, that is what we do it when you consider the fixed control volume. But if you consider that I have a movable control volumes, like for examples, I have the ship which is moving with velocity v. So, we can consider a moving control volume. That means, I have the velocity v and I try to find out what could be the drag force acting on this or the lift force is acting on this, how the turbulent structure is created by this ship and what that effect is going to do on ecology of the river, which is next level of the fluid mechanics problems what we have been discussing in this present era. We follow simply a movable control volume. That means, the control volumes is moving with a velocity v, and you try to find out for this control volume what could be the velocity distributions at the relative level, because v is moving it. So, you have to use relative velocity components to find out the velocity field and all. Same concept what will be used. Similar way, we can talk about a deformable control volume, which is generally used for the fluid mechanics problems in a mechanical engineering, like there is a piston movement is happening it and within there is a gas, and if I consider this the volume, the space occupied by this gas will be deformed it also the movable. So, this very interesting concept that we can have the control volumes three types: fixed control volume, movable control volume or deformable control volume. How to define that? That the problems what we have considered, whether it is ship in motions or fixed nozzle or movable piston case, that is what we will have. But we have use a control volume concept to solve these problems. That is again I want to highlight it, that try to understand any of the problems what we have. I have just given a 3 example, we can solve it if you can use a control volume concept. And the control volume can be a fixed, that means it remains at that same regions, does not change its positions, or we consider a control volume which is moving with velocity v, or a control volume which is expanding, deformable. Okay. Volume is changing it, volume is changing it with respect to time, volume is changing with respect to, then it is a deformable control volume. So, we have a fixed control volume, movable control volume and deformable control volume. Okay, let us have just few examples to show the difference between system and control volume. As you look at that, if you have the fluid which is there inside these engines can be considered is at the time t1 is a system. That means, whatever the fluid particles are there, they are representing a system, and that space we define as a control volume at the time t. But after t2 times, your control volumes remains at the same place. the system has gone at different locations can have a different shapes. That is what very interesting figures what is there. The same way if you talk about a balloon filled with gas and whatever the gas particles are there, that what we you consider is a systems, and the space what we have considered the control volume, and we just open up the balloon, we can have a systems will be in two places. Okay. In the T2 times the system can have it, but you have a depermeable control volume which is representing this part. So, if you can understand now with these two figures that we can simplify very complex problems with a depermeable control volume and also the moving control volume concept, which we should try to understand that how we can simplify it when you consider the depermeable or the moving control volume concept, which that is what is the art of the fluid mechanics persons to define it, with what respect it can define the flow systems using control volume concept, either a fixed control volume or the control volumes which will be the moving with the velocity v. The v could be in a vectorial forms, it can move it any directions, any magnitudes. Similar way it can have a depermeable control volume as it is given the example here. So, you can understand it, you can make it complex problems using these three tools: type of control volume, fixed control volume, movable control volume and depermeable control volumes. Now, let us coming back to, as you know from your 12th level of knowledge in fluid mechanics as well as the solid mechanics, the three basic conservations law we follow it, which is mass conservations, momentum conservations, which is the part of Newton's second laws of motions. Then we have the third laws which talk about energy conservation, is the first law of thermodynamics. Now, let us talk about that when you consider a systems, that means these three conservation principles, that what is quite valid. When we consider a isolated systems, like as I given a example, the virtual fluid balls are the isolated systems. Okay. They can move at different time. Okay. Like for examples, if I consider a systems of a set of the fluid particles or a set of virtual fluid balls, as you can understand it, there is no change, no other type of mass decaying function is there, the mass will remain the constant. That means, what will happen is mass at the system level at T1 is equal to mass at the system level at the T2 will be the same, but they can have simple space what is at this location, but when you come it to a T2 level, they can fragment it, they can occupy very complex surface at T2 times. So, at the mass conservations, it is a very simple things that you just know it, the mass remains constant at T1 and T2 time if you are considering a system. That means, if you are considering a isolated systems where you have n number of the fluid particles or the virtual fluid balls, that numbers will be remain the same whether you have a T1 time or the T2 time. So, that implies us that the conservations of mass is hold good. So, that very basic concept what we have been used it for solving the fluid flow problems when you consider the fluid systems. Now, come it as you might have solved a lot of physics problems on solid body translations, rotations and all, the basic concept of the linear momentum equations you apply it, which is you know it, force is equal to mass into accelerations or mass into dV by dt, okay, or change of rate of change of momentum flux. That what will give it the force into mass into acceleration. That's what is the Newton's laws of motion, second laws of motions, and you have been using that many problem to solve in 12th level of the class in physics or the fluid mechanics type of problems. Now, let us come to that what it happens when you consider as a systems, that if I consider a systems here, okay, which may be containing of set of the fluid particles, okay, and it has the two force component is there, and since as a system is moving a mass with a velocity v, after t2 times it can come to here. The change of these, the displacement of these system from one locations to other locations, it all depends upon how the net force component is working on that, what net resultant force is acting in that. That what is time rate of mass momentum is equal to the sum of external forces. In mathematically, what I have shown it that sum of the external forces which is going to act it, that what is mass into accelerations. That is the time rate of change of mass momentum m into v. Okay. Mass momentum is equal to the sum of external force acting on the mass. We know it, I have just repeat it to relate this when we talk about at the control volume level. Now, coming to the energy conservation equations. See, if you look at the energy conservations, you know very well energy is conserved unless otherwise you have a very particular cases. That means, if I have systems like for examples, I have a pump system here, okay, and it is connected to the inflow, also it is connected to the outflows. That means, two pipes we connected to that, I have a pump. So, if you look at that, the pump is giving energy to this fluid. Okay. We convert from mechanical energy to the potential energy to that. The pump is giving additional energy or work done by the mechanical to the fluid. Okay. So, we have an exchange of work to this system. Also, as you feel it, if you touch any pumping system just the outlet level and the inlet pipe, you can see there will be a temperature difference what you will feel it. If there is a temperature difference, that means it is a heat transfer is happening it. So, work done is there and also heat transfer there. So, any system you consider it pump or the turbine, you can in a fluid flow systems you can say that the time rate change of the energy for a fixed mass of fluid particles, you will be sum of rate of work done, okay, and the heat transfer. As I have given the examples, that means, if you have a system T1, you can have a work done components coming in, going out, the flow is coming, heat is coming out, going out. The net, the sum of these ones, rate of work and the heat will change the time rate change of in energy. That is what you can have a system of energy at the T2. So, you can imagine it that you have the flows pipe systems in your hostels. So, at each point this energy of the flow systems are changing it. So, you have a overhead tank, you have pumping systems, you have pipes, there is energy losses in the pipes, you have the outlet points like sink basins. It is just a simplified, if you look at what is a pipe networks, you have to supply the water to your hostels, all follow the energy conservation equations. But sometimes some components are not that significant. For examples, in a 5 flow systems, when I have incompressible flow, the heat energy losses may not be that significant as compared to the friction losses in a pipe. So, that type of simplifications we do it, and that simplifications make it the problem to solve it. But try to understand it that whenever you have a systems and to conserve the mass, we will have a sum of the rate of work and the heat transfer. There is a heat transfer, the process is happening, maybe that its magnitude is more or the less, that what we consider, and because of that there will be a change in energy with respect to time. So, which is the first law of thermodynamics, as you know it is, that is what the first law of the thermodynamics. We are not introducing the new laws. The conservation of mass for the fluid particles levels, is you know it, it is not important because always it is conserved. The conservation of momentum, which is required for you to know it, how the fluid particles are moving it, what could be the force exerting on that, what could be the velocity. Similar way, we can understand the energy conservations, which plays the major role for us when the flow comes from one locations to other locations. How much of work done that by the fluid or into the fluid. Similar way, whether there is a heat transfer is happening it, which we can feel it, there is a temperature gradient, there will be a heat transfer either to the surrounding of the systems or into the systems or the out of the system. That what we can do. So, to summarize this, that means we all know it that there is a 3 energy conservation principles what we follow in solid mechanics when you consider as a systems. Same concept also we can use it for at the system levels to solve the problems, conservation of mass, conservation of linear momentum, which is Newton's laws, second laws, and the conservation of energy, which is the first law of thermodynamics. As I discussed it that there is system and the control volumes, let us understand the Reynolds transport theorems, which establish the relationship between the conservation law of at the system level and the conservation law at the control volume level. Now, let me define 2 type of properties we have. One is called extensive properties, another is the intensive properties. Okay. The extensive properties, which is considered as proportional to the amount of mass. Okay. When you apply it, extensive properties, that means you are talking about the properties which are proportional to the mass, amount of the mass. That means, as mass increases, you will have a extensive properties going to increase it. Mass decreases, the extensive property, it is a proportional to the mass. So, for example, as we discuss it in 3 basic laws, we talk about mass conservation, momentum conservations and energy conservations. So, M will be the mass conservations, what momentum and energy conservation. But when you look at that, the intensive properties, that means we look at it is independent of mass. That means, which is denoted as a small b, denoted as a small b by capital B by m, or in mathematically I can define it dV by dm. Okay. So, if you look at that way, there are 2 properties, extensive properties and intensive properties. In intensive property independent to mass, we are B by m, okay, per unit mass what you are talking about. Like for examples, for energy conservations, the extensive properties will be the 1, but in case of the momentum conservations, the extensive properties will be momentum, but intensive properties will be the velocity vectors. Similar way, if you look at for energy conservations, if you look at extensive properties, that what is energy, but intensive property is a small e, which is the specific energy. Specific energy, that means energy per unit mass. So, small e is independent to the mass, amount of mass in the control volume or systems level. So, we define the difference between extensive properties, intensive properties. Extensive properties we define as a capital B, intensive properties we define as a small b, and they have the relationship simple relations like this, and mathematically dV by dm. Okay. That what is the relationship with that, and we define the difference between the extensive properties in 3 case: mass, momentum, energy, but that correspondingly for intensive properties which is independent of mass will be 1 velocity vectors and small e stands for specific energy. So, now we will go to derive Reynolds transport theorems. The derivation of the Reynolds transport theorems are available almost all these fluid mechanics books. Okay. The idea for me is that to introduce the Reynolds transport theorems that you can easily understand it, but the stepwise derivations, if you are not understanding it, I could suggest you follow any of the fluid mechanics books, okay, F.M. White, Sinzel-Simbala, or any other fluid advanced fluid mechanics book. You can see the derivations of Reynolds transport theorem. Only the symbol of representations of extensive properties, intensive property, either the capital B or small b or beta used in different book in different forms. Otherwise, the Reynolds transport theorems, which are basic equations, are the derivations of basic equations is available almost in all fluid mechanics book. Now, let us coming to the derivations, which I will highlight it as I said it, while derivations which are the major components, not by the line by line. Okay. So, first what I am considering as a non-deforming control volume. Okay. And this is what my non-deformable control volume, and also I have drawn the streamlines, they representing the flow what is coming in and coming out. So, if this is my control volume, I can define there will be a control surface defined by A, D, C, F. This is the dash part is defining me a control surface, and this what it is indicating me. These lines are the streamlines are indicating is that how the influx is coming into the control volume, going out from the control volume through this surface, that is what my control volume. That means, whatever the fluid particles present at the time t, that what will be represent me as a control volume, and that the regions are is a fixed. Let me have a very simplified case. I will consider that is the system for me at the time t. That means, I consider at the time t whatever the fluid particles are there within this control volume, that is what the system, as you already I illustrated, at the t plus delta t time, at the next instant of the time, okay, definitely the fluid particles they will move it, as we can see from the velocity vectors, they will move out from this and they can occupy this space. Okay. This can occupy this space. Now, I can define this 3 into 3 different space, like the space defined by this part I can define as I, and this can be double y, and this can be used as the control volume space, which is the space is occupied at the system at the t time as well as system at the t plus delta t time. So, I have defined these regions into 3 parts. One is the influx regions, another is outflux regions, another is the common regions which is there when the system at the t time, also t plus delta t. So, there is a influx regions, there is outflux regions. So, at the system level t plus delta t, I can define it as a control volume level of t plus delta t. The positive and negative you can understand it, we are defined in terms of in or the out. Okay. That what the sign convention you can try to understand it when I talk about the velocity and area dot products, that what will be influx and outflux will be a different sign, that what we will discuss it. Now, if you look at, if I look at simple definitions of the calculuses, that the time rate of change of the B in the systems as a definition t plus delta t minus the system at the t level, and I just apply what I have derived the 3 components at the 3 regions, replacing to these values. Again I know it, the B value of extensive properties at the T is equal to the B value of extensive properties of control volume at the T. So, I replace this value at the system to control volume level. If I do it, if I just do a rearrangement of these equations, I will get one part, you can understand it at the control volume levels, which is showing it B control volume at the T plus delta T time, B control volume at the T time by dt. That means, it is what is the time rate of change happening at the control volume level, that the definitions were indicated. And we have a other 2 part, which is a representing influx and the outflux of these regions of region 2 and 1, T plus delta T by dt and T plus delta T by dt for B 1 and B 2, which are the different regions, or the influx and the outflux regions. So, you can understand it, we can dB by dt at the system level can componentize 3 parts. Now, I will discuss these 3 parts to simplify it. Like, let us look at the examine this part. Okay. What is the time rate of change of B 1 at the T plus delta T time or B 2 at T plus delta T time. And as you know it, at time equal to T, B 1 T equal, that what is a 0 and B 2 T also 0, because at the time equal to T there was no flux inside that is what is 0. So, there is no 0, that B 1 and B 2 regions is the 0 level. If it that C, so the B plus, if I consider this part, now the same B 1 T I can write it in terms of these ones, as I know is B 1 T equal to 0 by dt. What is representing this? That is what is representing rate influx of B through the surface of AFC. Similar way, you can find out B 1 T plus delta 2 B 2 delta 2 can have a B 2 delta T by B 2, which will be the, again it will be rate of outflux through this ADC. So, the 2 component we defined it, one is a representing influx, another is representing the outflux, how much of rate is happening through a surface of AFC or the through the forces of ADC. That what we represent. There is a small mistake here, this is B 2 not B 1. Now, how to compute the outflux surface? Okay. That means, assuming it is a 3-dimensional control volume, 3-dimensional control volume, and over that surface I have to integrate it, I have to know it how much of influx is coming into the control volume or going out from control volume. That means, I can take a small area dA, okay, and I can have a normal vectors and I can have the velocity vector to that. Okay. So, if theta is less than 90 degrees, which is representing as the outflux, the flow is going out from this control surface. If I have these conditions of a dA area and this, and I try to compute it, what could be the flux going out from this surface at time delta t, during the time delta t. That part, if I look at very simple things, the same element area, I have the velocity vectors, I have the n is the unit vectors, normal unit vectors of these things. And if we have in a delta t time, if you know this velocity v, then the length of these, the imaginary surface volumes will be the v into dt, velocity into time, we will talk about the length. That means, what is the volume of the space is because of this outflux, that will be the v into dt, that is what the length, and we know this area. Now, we have to compute it, how much is coming through this oblique cylindrical surface, which you have a dA area and time during time dt. You can have dB equal to b into dn, dm representing the mass, elemental mass. The mass will be the density in times of the volume of this surface, the volume of this surface, and the volume we can have a simple geometry, we can use it to find out the volume, which will be the area into the length. Then we can find out the length projections, then we can convert the length, the dl into v into dt. So, we will get it dv will be this part. If you have a time rate charge of the dv, if you look it, you get this part which a dt is cancelled out. Okay. And if you look it, v dA cos theta is nothing else, is a dot product of the velocity vectors and the unit vector into dA, which is the outflux representations. We can represent as b times of rho, rho is the density, b the dot product of the velocity and the unit vector dA, that is what is the outflux, the change rate of change of the outflux going through this dA area. Since I have is a big control volume and the surface is irregular, then I can integrate that through a surface of ADC to get it total outflux rate what is going from this control volume. So, if you can try to look it with a simple geometry, we can find out the how much of total outflux rate is going out from this control volume, doing a surface integrations, where b dot is the b small b and the rho is the density, and the velocity, the dot product of the velocity at the dA. If I do the integrations, then I can find out what is the amount of the total outflux rate is going out from this control volume, either mass conservations, mass, momentum flux or energy flux. That what we will discuss more as I proceed. Now, we look at the similar way, if I want to compute it how much influx is coming it. So, you can understand the velocity will be inward and the surface unit vector will be outside and outwards it will be theta will be that. And same way you can get it, only this sign conventions will be the different, nothing else. Okay. The same way we can have a to find out the total influx coming into this through this control surface will be a surface integral with respect to AFC. The sign conventions indicate which directions is going on with a dot product of the velocity and the normal vectors of the surface area, and then you get it dA part. So, the same derivations, as I said it, you try to understand the derivations what I am talking it. If you have any doubt, you can follow up any of the fluid mechanics book of the chapter of Reynolds transport theorem. Now, coming to the third part, the first two terms, that means we can write it as earlier. You will have the influx and the outflux, that what can be written as integrals of influx and outflux, and if you combine it at the next what you are getting it, this is total cross sections. Okay. That means net outflux of mass, momentum or the energy flux going through the system, either influx or the outflux, but as you integrate it, it represents net outflux what is going through this control surface, as if I know the velocity and the unit factors, if I know the B and if I know the density, how varies it. So, then we can find out that what could be the net outflux is coming out if I am doing a surface integrals of these functions. Okay. It looks easy, but it is not that easy. That is what my idea you to understand the problems better way. Now, if you look at the last terms, which is very simplified form, if you look at the definitions wise, what is this? The change of the B value, extensive property at T plus delta T level minus of change of B value at the T time by dt. That means dV C by dt. That is what is simple definitions. How to compute the BCB? What is the total extensive properties in the control volume? That means you can do a volume integrals of the small control volume what you have considered here. If that is a rho is a density, the dm and db is the mass and this, that means we can just integrate it this part and we can have a this part. See, very simple definition is density times of the volume is the mass. Okay. So, your dm is equal to rho dv, v is I am scratching it showing it is a volume not the velocity. So, rho times of dv equal to dm and b is intensive properties. If I integrated the volume integrals over this control volume, then I will know it what will be the BCV. Okay. That means, the time rate change of the control volume in mathematically we can write it this is. That is what just substituting BCV at this point, it is a time rate change of the control volume. This is the volume integral of B density and the dV. If I do it that what will be represent me the rate of change. Now, I will just use these three terms to form Reynolds transport theorem, which we are just discussing. That means, the system level of the change of the B value is at the time rate of change of the B value at the left side is equal to the what is accumulations rate of change of the B value at this control volume level, which is indicating are a volume integrals of B rho dV, how much change is happening at the control volume levels, how much net outflux of B through this control surface, that is what is indicating here. Okay. And sometimes we use a total derivative to represent that once. So, if you look at that dV by system by dt, we can have these systems to define it. As summary to that, I can say that time rate change of the B in the systems is equal to at the control volume levels accumulations rate of the B value in the control volume net outflux of the B through the control surface. So, we remember it the velocity what you observe in the control volume level, or I will talk about how we use the relative velocity component when you go for control volume moving with velocity v, that we look at very complex problems. So, this is what the Reynolds transport theorems, and the basic physics you can understand it that we are relating with a system level and the control volume levels. That means, Reynolds transport theorems now, if you have a system, you have a control volume, and very simple represents this, the relationship is developed by Reynolds transport theorems, which is very looks like a very mathematically very complex problems that we have now. We have a volume integrals, we have a surface integrals, we do not know how density varies it, how the velocity varies it, and how it is related with a system to control volume level. But this is what my duty to simplify this problem, these complex equations and solve many problems. That is what I will do it in coming 5 to 6 lectures. Let us coming back to very simple case what we can do it, the steady incompressible flow. Okay. If you consider a steady incompressible flow, but that means the flow does not change with time, also the density does not change with the space and the time. Density changes it in this case of the steady compressible flow. If that is the conditions, okay, your major part of this becomes 0, because if you d by dt becomes 0, that means you have the, let you consider this case, I have V inlet is coming, V outlet is going out, and I have a pumping systems. If I consider the V inlet is a constant, okay, you can observe it, your V outlet will be the constant, will be the steady state will come it. If you make it, the inflow is a constant. After certain times, if you look at the V out is a constant. So, there will be no change, there will be a flow, but there is no change of the velocity influx at the outflux. Then what it indicates that there is not net change in storage or accumulated mass momentum flux within the control volume, that becomes 0. If it is that, then dB by d systems is equal to the this part, which is just we want to do a surface integral to solve it, how the system is changing it or the control volume level. So, that is what is the simplification if you use steady compressible flow. But most of the time as we use the steady incompressible flow, okay, density is constant, the Mach number what you consider is the flow is less than 0.3, then your density will come out. So, the problems is become more simple is that you just do for integrations of velocity and the unit vector products with the B value, which is could be a specific energy, could be the velocity vectors or could be the 1. So, the problems become simpler when you consider steady incompressible flow. What I want to emphasize is that the student has to understand it, how to simplify the problems, whether he has to solve the problem as a steady compressible flow or steady incompressible flow, or you make it to tell unsteady compressible flow, which is again you have to do a volume integral to solve this. The simplifications is matters a lot to solve the problem as compared to use the advanced mathematics that try to understand it. That is what I will try to give a lecture on that how you have a develop a art to simplify a complex problems using the control volume concept. Let's with these things, let me summarize today's lectures. We discuss about system and control volume, we talk about fixed and deformable and moving control volume concept. The more important is that we establish derive the Reynolds transport theorems, which can use for fixed control volume, deformable control volume, moving control volume. And we also demonstrate that the use of the simplifications of the steady problems, we simplify the problem as compared to go for unsteady incompressible compressible or compressible unsteady compressible flow, which are complex problems where we need to integrate surface integration on the volume integrations and solve these problems, which is more complicated than these things. So, we can have a conservation of mass, linear momentum, energy equations, we can derive it from RTT, that what we will do it in the next class. And as a system wise, I can again put is focus on the set of the fluid particles. Here talk about the region of the space which is bounded by or surrounded by the control surface. We will discuss more details about how RTT will be used, derive these mass, linear momentum, energy equations in the next class. Thank you a lot for this.